Hello again. We've got a new thing here today that is called energy diagrams, and we use these to represent a reaction and show what happens to the chemicals inside it as far as their energy content. So when we draw one of these, we have energy on the vertical axis. This is how much energy is in the chemicals, and the horizontal is what they call the reaction axis, and it's kind of a time axis. What it represents is the situation before the reaction starts and after the reaction's over. And some of them just have that, but some also have a level in the middle that shows what's happening during the reaction. And so we can read a number for the energy content of the chemicals before. That seems to be 20 kilojoules. During the reaction, we get up to 70, and after the reaction, it looks like we're at 40. And the first thing they ask us is, would this reaction be endothermic or exothermic? If you're thinking about that, all you care about is how much did the energy change from the beginning to the end of the reaction? And if it went up, we call the reaction endothermic. That means the chemicals gained energy. And if it dropped, if you had a graph that went like this, then from your beginning to the end would be a drop, and we'd call the reaction exothermic. Endo sounds like into, like energy going into the chemicals. Exo sounds like exit, like energy coming out of them. So this reaction, because it goes low to high, is endothermic. Next question, okay, how much is the energy change? We said the energy went up, but how much did it go? It went from 20 up to 40, so our enthalpy change is plus 20 kilojoules. If it dropped, if you had a diagram that went like that, then we'd say we were higher here, lower here, and so our delta H would be a negative number. Now, activation energy is a different thing. Activation energy is about how difficult it is to get from the beginning to the end. So for this, imagine you're standing here on the left side, and you want to go in the forward direction, meaning you want to go over to the right on this curve. How high of a climb would you have to make to get over this bump? You're starting at 20 kilojoules. The top of this hill is 70 kilojoules. So from 20 to 70 is a climb of 50 kilojoules. That amount is called the forward activation energy. It's how much energy you have to pay to get over the top of this bump. After you're here, walking on a flat surface is free, and dropping down like this is free. Think of it like a mountain where you could just sit down and slide once you get to the top, but you have to work to get to the top first. So here we would say the forward activation energy, which usually gets a symbol like EAF or EA forward, is 50 kilojoules. It's a positive number because we climbed up. The reverse activation energy is the same idea, except now you're over on the right side and you want to go home. Now you are here, and you have to climb up this, and then the flat is free, and again the drop here is free. So now you're starting at 40 kilojoules, and you have to climb up to the top of the hill is still 70. From 40 to 70 is a climb of 30 kilojoules, so we could say our energy of activation reverse is plus 30 kilojoules. So the delta H is just beginning to end, and any activation energy is how difficult is it to get over the bump in the middle. Good. Let's try it again. This one they turned it around. Now it's our turn to draw the energy diagram, which means we might have to make up some numbers here. They start us off with draw an energy diagram where the delta H, or the delta E, this is enthalpy change, is minus 150 kilojoules. So we're starting somewhere. Actually, I want to have space above this. We're starting somewhere, and we need to end up 150 kilojoules lower than that. So this reaction's a drop. Let's get some numbers on this before we get any further. 0, 50, 100, 150, 200, 250, 300, 350, 400, 450, 500, 550, 600, 650, 700. Okay, so if we're going to show a delta E or a delta H of minus 150, actually I've kind of had it there. If we start at 200 kilojoules and we drop to 50 kilojoules, that would do it. That would be a drop of 150. Where did I get this number? I completely made this up. I just wanted a couple numbers that were 150 apart. So I picked, you could go 150 down to 0 or 500 down to 350, anything you want. As long as the difference between them is 150, you're fine. Now, they want something else here. They also say they want an activation energy of 450. So for this, imagine you're standing here. And to get over the bump in the middle, you would have to climb 450 units. So now we have to add that in. Starting from 200, we have to go up 100, 200, 300, 400, and 50. That's the height of the middle bump. So all of this is 450 kilojoules. Okay. From here down to the end is minus 150 kilojoules. That's the first number they told us to build into this. Second number is the bump in the middle. And that's just about all we need to draw this thing. Now, they also want us to label some pieces on it, which is easy enough. A and B are our reactants for this weird made-up reaction. So we would put those over on the left side. We start with chemicals A and B. C is our product. So on the product side, after the reaction's done, we have chemical C. And the in-between part is what we call the transition state, or sometimes they call it the activated complex. Transition state. If you think of chemical reactions like Lego bricks, then this reaction could be something like, in the Lego box right now, you have an airplane and a bear that your sister made, but you want to make a castle. There's two steps to doing that. The first step is take the airplane and the bear and tear them apart into individual loose pieces. Then put those pieces together and make your castle. The taking things apart step is what we call the activation energy. That's where you're putting in work to do this. It's not a lot of fun. You're just tearing pieces down. And then the fun part, where energy gets let out, is the part where you build the thing you wanted to build in the first place. And the transition state is when you have all loose pieces. You're exactly halfway done. You've done all the taking apart, and you're about to begin the putting together step. Okay, now that we have all that, let's see if we can knock down these questions. Is this reaction endo or exothermic? What do you think? It started here. It ends up down here. Because this is a drop, we would say the reaction is exothermic. The chemicals lost energy as this was happening. Determine the reverse activation energy. That would be, pretend you're down here on the right side, and you want to go home. You want to climb back over this bump and then slide down this side to get home. You're starting at 50 kilojoules, we said, and you're climbing up to the top, which is at 650 kilojoules. So overall, the climb should be plus 600. I apologize, the labeling on this is not fantastic, but when I was drawing this, I found that the top here had to be 650, and I said the beginning was 200. And again, I made up these numbers just to get a diagram drawn. Your numbers could be totally different as long as the distances between are the same. Everything will be fine. So reverse activation energy, we could say EA reverse is positive 600. And now they bring up a new thing. A catalyst speeds up this reaction by providing a different mechanism. How would this change the energy diagram? A catalyst is some helper chemical that makes a reaction go better. And on the energy diagram, what they actually do is they lower the bump in the middle. So if this curve that I've drawn is the basic natural reaction before we change anything about it, this is before, the catalyzed reaction would start at the exact same place, and it'll end at the exact same place, but in the middle, it won't have as high of a bump. So you get a lower energy for your transition state or your activated complex. Now that means your forward activation will be different now, and your reverse activation will be different now because you're climbing a lower bump. But, very important, your delta E or delta H is exactly the same as before because that's only about your beginning and end points. The delta E or delta H doesn't care what this middle level is. If you're calculating that, you'd still say, I started at 200, I ended up at 50, so this number is still minus 150 kilojoules per mole. The exact same as we had before. Makes no difference how high the bump in the middle is. This only affects the activation energies. Fair enough. Generally on our tests, in case you're worried about this and the numbers that I made up, we don't generally get you to draw one of these because there are an infinite number of answers and that's a nuisance to mark. So much more likely we will give you a drawn diagram and ask you questions about it. We'll say, is this endo or exo? What's the delta H? What's the reverse activation energy? What would a catalyst do to this? Or which of the following could be the catalyzed energy diagram? Things like that. So it's good to know how to draw one of these, but I know making up the numbers makes people a little uncomfortable. You won't need to do that, except maybe in practice, but not when we get to tests. Hope you find that comforting. Okay, this last question's a little odd and unusual, but let's make an effort with it. They give us a reaction, doesn't really matter what the chemicals are, and they tell us that its delta H is plus 61. So we start somewhere, I don't know where, and we end up a little higher. And the difference between these is 161 kilojoules. I'll make up some numbers just to maybe make this work a little nicer. We'll say this is 100, and so this other number would, of course, be 161 kJ. Okay, that's our delta H of reaction is plus 61 kilojoules. Now, these we don't talk about a lot, but they say the enthalpy change of the decomposition of the reactants is plus 111. That's our forward activation. It's another way to say that. That's the part where you take the things your sister made and tear them apart and make loose Lego bricks. They're telling us that this is 111 kilojoules. So if we started at 100, this must be 211. 100 plus an extra 111. Our transition state is up here. Transition state. And now they're asking about what's the enthalpy change for the formation of the products from elements. In other words, what's the delta H, or the enthalpy change for when we take our loose pieces and put them together. In other words, this amount. They say, how far is that? Well, we're starting at 211. We're dropping down to 161, so this distance must be 50 kilojoules. It cost 111 to tear everything apart. We get 50 back as we reassemble the pieces. And now I think all of these make sense. We have a total difference of 61 going from the beginning to the end, plus 111 going up, and 50 going down. These are hard to do if you don't make up numbers on the left. You end up labeling a bunch of distances with arrows, and it's a little bit messy. But I hope it makes sense how you can figure out each of these numbers once you have the diagram. From our beginning to the end point is a distance of 61. From the beginning to the peak is a distance of 111. That right there is 111. And the drop on the other side ended up being 50. Another thing, these symbols, the textbook uses these a lot, like delta SD and there and delta RH. They write these subscripts like there's a standard set of them and like you should know what all of these mean. There's a lot of latitude in how you make up these subscripts, and don't worry about memorizing these. You should not be able to glance at this and go, yes, the simple decomposition enthalpy change. We don't use these a lot on the exams either, and if we do use one, we will explain it very carefully. So please don't worry too much about these. The textbook loves them. I do not love them, and we won't let these hurt you when we get to the testing part. Main takeaways: you can measure these distances from the beginning to the middle bump to the end, and from those you can get 3 different values for a reaction. What did it cost to tear apart the reactants? What do you get back when you reassemble those into the products? And what's the overall difference? If you can find those, you are good.